Hello, everyone. This is the second episode of my podcast, where we talk with interesting people about deep tech and recent trends in technology. My guest today is Paweł Gora. I'm really pleased that Paweł accepted my invitation. Paweł is a scientist in the area of machine learning, artificial intelligence, but most of all in the area of quantum computing, which is a major trend in computing today, probably still in its infancy, but we will also talk with Paweł how it will develop in the future and how quantum computing looks today. So thank you very much, Paweł, again for accepting my invitation.
Great.
And
thank you, Maciej, for sending invitation. So it's my pleasure to be here, and yeah, I'm looking forward to our interview.
Right. So Richard Feynman was a renowned physicist and one of the major inventors in modern physics and in quantum mechanics. Said that if you think that you understand quantum mechanics, you don't understand it at all. And quantum computing is application of quantum mechanics into the world of information technology. So would you start shortly with describing what is quantum mechanics and how it transforms into quantum computing?
All right. So, of course, it's not easy to just briefly explain what quantum mechanics is, because as you said, as scientists, we still cannot say that we really understand quantum mechanics completely. Because when we start thinking about quantum mechanics, it turns out that it's totally different than classical mechanics that we can observe nowadays. So when we observe our world, we can just build some mathematical descriptions, mathematical theories on how this world works. And I think that we should go back to the end of 19th century, when almost all scientists, or most of scientists, thought that the physics is almost a completed theory, that we know almost everything about the world. We had the equations of the electromagnetic theory, electrodynamics, Maxwell's equations. We had Newton's theory of dynamics. So researchers thought that we know almost everything about the world. But at the end of the 19th century, there were still some open problems in physics. And researchers thought that these open problems will be just resolved relatively soon. And it was expected that they will not lead to a totally different theory of physics and totally different description of our world. But it turns out that the discoveries made at the beginning of the 20th century led to the new understanding of our world in the micro scale, in the scale of just single atoms, let's say. So it turned out that the classical mechanics, the classical description of our world just doesn't explain the physical phenomena that were observed in the micro scale, in the scale of single atoms. Niels Bohr, a physicist from Copenhagen, formulated a postulate which basically says that the energy of electromagnetic wave can be emitted only in quantized form. So here we have this word quantum or quantized, which means that the energy cannot be emitted, or the emitted energy of the electromagnetic wave or photons cannot have just arbitrary values. So these values may depend on the frequency of the electromagnetic wave. There is something that was later called the Planck's constant, and there should be also a multiplier, which should be an integer. So there are only some very specific particular values of the energy that this energy of emitted photons or electromagnetic wave can take. So, and it was a huge discovery, and it later led to many other interesting discoveries in physics. And as a consequence, a totally new description of the world in the micro scale emerged. So later we had something like the Schrödinger's equation, which just also describes how.
If I may interrupt.
Yes. Okay. Yes.
Let's say what I remember from school, from high school, is basically that there are atoms and they are surrounded by electrons.
Mm-hmm. Yes.
Basically, to me, like a total layman, this quantum mechanics and its most important discovery, just to show it, let's say, somehow more visibly to our audience, is that we never know where the electron is.
Yeah. So we don't know until we just do a specific measurement, right? Or we can try to do a measurement, and then we can just say something about the location or about the spin of the atom, let's say, right? So this is one of the consequences. Was one of the consequences of the discoveries in the early in the beginning of the 20th century, right? So yeah. So and why it's important from a perspective of quantum computing and from computations, from perspective of computations. So when we just do research in quantum in just computer science in general, we are mostly concerned about algorithms, right? So we can analyze the complexity of different algorithms. We can try to prove the correctness of algorithms. But at the end of the day, we would like to implement our algorithms and run these algorithms on physical devices, right? So, and these physical devices are governed by the laws of physics, of the real world. And this real world or this physics, these laws are inherently quantum, right? So one of the consequences is that, for example, we cannot do our computations for free. So there is also a minimum amount of energy that should be involved if we want to just perform some specific irreversible computations, like erasing one bit of information. So this was later called the Landauer principle. And also we cannot just build computer elements that will be arbitrarily small and at the same time operate in exactly the same way as they operate nowadays. So I believe that at least some people in our audience heard about something that is called the Moore's law, which basically said that the density of transistors in an optimal circuit doubles more or less once per 2 years. So currently, recently it has been already observed that this trend has slowed down. So now this doubling is more or less once per 2.5 years. At the beginning, so in the 60s of 20th century, it was a bit faster, maybe once per 1 year or 1.5 years. And it's expected that this Moore's law cannot just be valid forever, right? So in 30s or 40s of 21st century, the size of transistors will have to reach the size of single atoms, right? And in such a scale, the transistors would not be able just to perform in a way that they perform nowadays. So that's why we should already start thinking about some other ways of computing in which we can somehow enhance the power of quantum mechanics. And in 80s of the 20th century, there was an idea that maybe we could just encode information on atoms. And for example, we can assume that the state of a bit, right? Or as we will see, it will be in fact the state of a qubit, may be interpreted as a spin of the atom, for example, right? And then we may just try to evolve our system of atoms according to quantum mechanics, so according to the Schrödinger's equation. At the end, we can do a measurement and get some values, get the spins of atoms that could be interpreted as zeros or ones. And there was an idea of Richard Feynman, that the scientist that you cited, that maybe we could just perform computations in that way, right? So just by encoding information on atoms or in a small scale.
So it's like, let's maybe talk a little bit more about bits and qubits, because just like atoms or electrons are the smallest parts of materia, or probably not right, because there are neutrinos and even smaller
Quarks.
Parts. Though from school I remember electrons, but it was 25 years ago. Yeah. This comparison is like bits today are the smallest parts of information.
That's correct.
And bits have value either true or false. So if we don't go, probably we don't have enough time to go as much into explaining bit system to our viewers. Probably most of them know it in a way, but it's a model of writing down every number by a system of zeros and ones, and then it's say algorithm working the way in practice that wired circuits, let's say, open up or don't open up, whether they are given value of 1 or 0. And qubit is something like neither 0 nor 1.
Or 0 or 1 at the same time. in some sense, right?
Yes, so it's just like the famous Schrödinger's cat, who might have been dead or alive at the same time.
Yeah.
But qubit is, to me, I understand this as a layman, as a kind of probability value.
Yes, so I think that it's a good intuition. So in fact, if you want to be precise, we should say that the state of a qubit, so as you said, the bit is just a single unit of information, right? In classical computing. In quantum computing, we have qubits, and a single qubit, indeed, a single qubit may have some information about the state 0 and some information about the state 1. And based on that information, indeed, we can infer what's the probability of getting 0 or what's the probability of getting 1 after we do a measurement. So initially, before the measurement, we can say that this qubit, single qubit, might be in a superposition, the so-called superposition of state 0 and 1. So it carries some information about the state 0 and some information about the state 1. So to be more precise, if you want to be more precise mathematically, we could say that this information can be just interpreted as something that is called in mathematics a unitary vector in two-dimensional Hilbert space over complex numbers. But it's very difficult, right? So it's very complex. But what is important from the practical point of view is that based on this information, we can infer what's the probability of getting 0 and what's the probability of getting 1 after the measurement. And what's also important is how these probabilities may change if we apply some quantum gates. So that's also important.
So how could you explain that why qubits are simply just many times faster than bits?
Okay, so I would not say that a single qubit is faster than bit, but because the true power of quantum computing comes when we have many qubits, like hundreds of qubits, for example, right? So the reason is that, as you can see, so in case of a single qubit, we've already said that we can carry some information about 0 and 1 at the same time. And when we have n qubits, so for example, if we have 100 qubits, we can carry information not about only 100 numbers, but in fact about 2 to the power of 100 numbers at the same time. So if we have n qubits, we can carry information about 2 to the power of n bit numbers potentially. So that's the potential. So of course, everything depends on how we construct our qubits, right? What will be the initial state of the qubits? but there is a potential to carry information about all 2 to the power of n bit numbers just by having n qubits. So when you have n bits, on n bits, in a single time, in a given time, you can just you can store only information about a single n-bit number. You can modify this value, you can modify this number, but in a given time, you have only information about the exact one n-bit number. But in case of n qubits, potentially you may have some information about all 2 to the power of n n-bit numbers, all possible n-bit numbers, and you can potentially process this information about all 2 to the power of n n-bit numbers at the same time. And here is the potential for this quantum advantage, let's say, right? So quantum supremacy or advantage of quantum computing over classical computing, let's say.
Quantum supremacy, right?
Right.
So again, in layman's words, it's, let's say, achieving a state of computing power which is absolutely overwhelming classical computing power.
Yes, potentially yes. So yeah, there might be this, let's say, exponential speed up comparing to classical computing in theory, because I just said that there is such a potential, and now just taking advantage of this phenomenon is not trivial, because in fact we cannot say currently that we know some quantum algorithms for which we can formally mathematically prove that there will be such exponential advantage. So that's another thing. So this is why we investigate this domain. This is why we do research, just to try to just develop good quantum algorithms that can give us advantage. But in fact, it's not that certain that there will be such great advantage in the future. So it's also something.
19 that it achieved quantum supremacy. So the example was that a 53-qubit computer solved some computational problems in 200 seconds, and Google claimed that normally it would have taken 10,000 years. After the IBM counted it that there were some, let's say, some factors not taken into account. So this problem should have been solved in 60 days. Still 60 days versus 200 seconds is a huge difference. But is it a marketing trick rather, or do we really have something close to quantum supremacy?
Yes. So for sure, this is something that we should acknowledge, right? That Google just ran an experiment that was just feasible on quantum computer with these 53 qubits, as you said, and it has been proven that, or I think we can say that it was proven that just running or computing exactly the same thing would take really enormous time on classical computers, even the most efficient supercomputers that we have nowadays. But then when you analyze the use case that was involved in this experiment, it will turn out that this use case was rather artificial. So this experiment was just precisely designed to just prove that we can run such computations on existing quantum computers that cannot be run efficiently on classical computers. But in fact, there is no really practical application of these results yet. That's just because the fact that this use case was just designed specifically to prove this, let's say, quantum supremacy. So in fact, we are still waiting for some real-world practical business applications, business examples, for which we can say that there is a quantum advantage, quantum supremacy over classical algorithms. And it looks that we are probably still quite far from that point.
Do we have applications of quantum computing in real life already?
Yes, Yes, we have applications. We already have applications, but it doesn't mean that quantum computers can already compute something more efficiently than classical computers. So, for example, there are applications in logistics. So there are already known algorithms, quantum algorithms for solving some optimization problems in logistics, like solving the traveling salesman problem or vehicle routing problem or traffic assignment problem. Or there are some applications in finance or even applications in machine learning, right? Or applications to just design new chemical materials, new materials, new drugs. So there are such research works, and we know that we can already apply quantum computers in these domains, but it doesn't mean that quantum computers can be already more efficient than classical computers. There is such a potential, but it even hasn't been, in many areas, it hasn't been proven that such a supremacy will just appear in the future. So this is just rather a hope that we will be able to just take advantage of this enormous potential of many qubits. But in many areas, in many applications, it even hasn't been proven that this will happen with certainty.
So it's not that we are doomed to adopt quantum computing. It may be the case that this trend will somehow,
So I think that it's still possible that this trend will stop at some point, but based on the current trends and based on the technological advantage that we can observe and we've been observing over the last years, it's more probable that we will reach this quantum advantage in the future. We don't know yet when exactly, so at least I cannot say. I don't know when we can expect this quantum advantage, but I would say that currently it's more probable that we'll reach it than just that this trend will just stop at some point. But I think that we should still consider that potentially there will be no significant practical industrial advantage of quantum computers. So advantage in terms of speed up is one thing, but another thing is also the cost of quantum computers and running computations, both at the cost of just building quantum computers, but also later the cost of utilizing, and the whole maintenance of quantum computers. For example, the cost of energy, right? Because contemporary quantum computers should be run in very specific environments with very small temperatures, with just isolation from the environment, right? So just preparing such environments is also quite expensive. This is also one of the reasons why most of the quantum computing power nowadays is available in the clouds, in the cloud services, like cloud services from IBM or Rigetti or D-Wave. So we'll see. We'll see what the future will bring. I believe that it's rather expected that there will be this quantum advantage, a real quantum practical advantage at some point. But I think that we should still consider that this trend will just stop at some point.
And how about, if we reach quantum supremacy within the next, we don't know, but at least 5 years, rather 10.
Mm-hmm.
How would it impact, in your opinion, the development of artificial intelligence?
Mm-hmm. So there are some potential applications of quantum computers in machine learning and AI, because one of the natural applications of quantum computers is solving the so-called combinatorial optimization problems, or in general optimization problems. Because when we do optimization on computers, we operate on discrete values, on bits. So in fact, the all optimization is a combinatorial optimization. But and as you know, or at least some of you know, machine learning and AI is almost all about optimization. So even if we train our neural networks, we in fact look for the values of weights of connections between neurons in order to just minimize a given loss function. So basically, this is how this training, or that's what's the goal of training neural networks. And there are different algorithms like backpropagation algorithm, but there are also research works just investigating how to do it more efficiently than using backpropagation. There are already some researchers claiming that we should forget about our current methods of training neural networks, and potentially quantum computers might enhance, first of all, the process of training neural networks, but also the design of some machine learning algorithms. For sure, there is a potential to at least speed up the process of training of neural networks. In general, training of machine learning algorithms. So this is one thing. Another thing that there might be potentially totally new applications of machine learning because with time we'll have more and more data from some quantum experiments, and then again, machine learning algorithms, classical or this hybrid quantum classical algorithms can be applied to just analyze the quantum data as well. Maybe one more important thing is that I expect that at least the initial application of quantum computers would be rather hybrid. So for sure, there should be some integrations, combinations of classical algorithms and quantum algorithms in a similar way as we have in case of GPUs, for example, when we train machine learning algorithms using graphical processing units. So some computations are first run on classical processor, then we have to prepare data for GPUs, and then we run some computations like training on graphical processing units, then we get the output, and we have to interpret the output somehow, right? So I believe that in case of quantum computing, it might be the same. So quantum computers can be run for just some very specific applications like optimizing some elements, some parts of computations. So that's the guess. But I can say that there are also some other, beside the optimization, quantum computing has also potential to generate some new data, new information, like generating art. And currently, both AI and quantum computing are also applied to generate music or some images. So these applications are mostly known in case of AI, but I've also heard about research works showing how quantum computers can be used to do it. And one of the reasons is that quantum computers can potentially sample data from probability distributions that are difficult for classical computers. So the Boltzmann's distribution is an example of a distribution for which it's computationally difficult to sample in case of classical computers, but we can easily sample from the Boltzmann's distribution in case of quantum computing. So randomly generating some data, right? So there's also potential in this domain, and it has been already shown that this may find applications, for example, in generating music.
Right, this is very interesting, but maybe let's go back a little bit because I think we can touch this topic, and it's a very interesting one. It's also about optimization, optimization of quantum algorithms. So quantum error correction, this is how it's called?
Yes, that's correct. Yes. Yes. Okay, I can just try to elaborate on this topic a bit. So this is one of the reasons. So the need for using quantum error correction is also one of the reasons why I said that it's possible that we'll not reach this quantum supremacy, at least in the near future, because when we read some announcements of companies working on quantum computers that, okay, they have quantum computer with 100 qubits, for example, then we should keep in mind that these qubits are physical qubits, which means that, okay, they are physical qubits, but when we just do some computations using these qubits, it will turn out that there is some noise involved, right? So there might be some errors of computations. So then we should introduce some error correction codes. But in order to implement these error correction codes, quantum error correction algorithms, we should use some of these physical qubits. And it may turn out that in order to build just a single logical qubit, that would be the ideal qubit, operating exactly as the theory of quantum computation predicts, we may need maybe even tens or hundreds of physical qubits. So it is possible, and it would mean that, in fact, in order to get or to reach this true quantum advantage, we may need quantum computers with, let's say, hundreds of thousands of physical qubits in order to just do this quantum error correction and get real ideal logical qubits that could perform computations without noise or with very, very small noise. But at least one of the good things is that we already know that some quantum error correction codes exist. And this discovery was also one of the reasons why people started believing that building quantum computers, scalable quantum computers, is possible at all, and that this is rather just the engineering challenge, how to do it, and not a scientific challenge, because we know more or less how to do it, but there are still many engineering challenges, like ensuring this correct quantum error correction, for example, right?
Yes, and we could dig into this. This is so interesting, but we have limited time scale here. So let's go to the topic, which is quite visible in the media. It's a common statement: quantum computing can break blockchain. To simplify it, so the impact on IT security of quantum computing is huge.
Yes.
Could you add on?
Yes. Yes, that's correct. That the impact of security and cryptography might be huge, and in fact is already huge, because in 90s of 20th century, I think it was 1995, it was proven that we can just break some very popular cryptographic algorithms, like RSA algorithm that is frequently used currently in many cryptographic systems, using quantum computers. So the reason is that many of the popular cryptography algorithms are based on the assumption that factorizing large numbers is difficult for computers. And in fact, it hasn't been proven even for classical computers, but people believed that it's true. So that's why we built some cryptographic algorithms based on that assumption that this problem is difficult for classical computers, even though it hasn't been proven. But it has been already proven that for quantum computing, this problem will be relatively easy. So there is the so-called polynomial time algorithm that can just factorize any arbitrary number, which indeed may break many of the existing cryptography techniques and encryption methods. But luckily, there's already ongoing research on cryptography techniques that could be just secure even in the quantum area. So there are methods that are based on lattices that are not based on the assumption on difficulty of this factorization problem. So we, as researchers, we already know that it might be possible to just ensure security of data. And in case of blockchain, as far as I remember, it was also proven some time ago that the classical initial blockchains can be can be broken using quantum computers. But I heard that later there were some advancements in this domain in terms of ensuring security of blockchain, even in the quantum area. And as far as I know currently, it's rather expected that blockchains will be secure. So so it will not be possible to just break these encryption methods in blockchain using quantum computers as well.
So this makes a very strong case for blockchain, to be honest, because there is a huge debate. Let's say, what's the role of blockchain in the future of economy? So blockchain is, unlike a printed money, is an asset. So
yeah,
the other day I made a post on my blog about it. That some people say that blockchain will kill inflation as an economics phenomenon. Very difficult to say, because let's say money becomes an asset again and not something that can be printed out by central banks with big business, Wall Street, dealing with it in the background. So maybe I would just ask you, what's your general opinion on how blockchain is important phenomenon today?
So to be honest, I don't have strong opinion because I'm not an expert in blockchain technology for sure. So for me, it's really hard to say. So from technological point of view, it's also it's very interesting, right? So the theory, the math that is behind this technology is very interesting. So from this perspective, I can say that okay, it's very cool, right? But at the same time, there are many other aspects, like economic aspects, maybe also social aspects, maybe also security aspects as well involved that should be taken into account, and maybe even political aspects. I'm not sure. So for me, it's hard to say what will be the future adoption of the blockchain technology and cryptocurrencies in particular. But I expect that there might be some interesting applications. There are already some interesting applications of blockchains, and I expect that this technology will be also developing further.
Recently I met a person who's an IT professional, but also a huge art collector and very passionate about art. And of course, we talk about tokenization a lot these days, but I've learned that there are companies who are tokenizing art already.
Yes.
Which would say it's all making things that were not accessible to the people, like buying an expensive work of art, affordable in some way, popularizing everything. Let's say this is an incredible topic. Which I'm touching this topic because apart from being a scientist, you are also an entrepreneur.
That's correct. Yes. So I have already founded or co-founded 2 startups. So I was not the leading person there. I was not CEO, and I was not even in the board of the startups, but rather as the advisor. I served as an advisor and co-founder, technical or scientific co-founder and advisor. In one startup, we're working on AI-based dialogue search engine for e-commerce. So the idea was that we may have artificial intelligence that can just search for certain products on the internet for us, and we can just communicate. Pardon, could you repeat?
What is the name of this startup?
Letme AI.
Okay.
All right. Another startup is Broomee Technologies, and in that startup, we are working on van pooling services. So by van pooling, I mean the vans or buses that can be just shared and ordered or requested using mobile application, and this can be just extension of the existing public transport in the urban areas in which the public transport is is not efficient enough, or in which it's not reasonable, it's not optimal to just add new lines of buses or trams with static routes. So this is rather the transport on demand, similarly to taxis, but in a model in which it's an extension of the public transport, and it's also adjusted to passengers' needs. So there are also similar ideas in several other countries as well.
So what is the name?
Broomee Technologies. So
Yeah.
that's the name of the startup, and the product is called Broomee. We already have one real-world implementation in Działoszyce. It's a gmina it's a region in Poland, in Świętokrzyskie Voivodeship, and we are now also looking for some other areas in which we can implement this technology.
And you said that it was let's say, quite a lot of interest for this product, more outside of Poland than in Poland.
Yes, we also had some talks, for example, with cities in Scandinavia, but also with some cities in Poland as well. So it became much more difficult during the pandemic crisis. So we had some implementations in plans just before the pandemic, but then when the pandemic came and the lockdowns, it turned out that shared mobility is not something that should be done and implemented during the pandemic crisis. But now everything is going back to, let's say, normal or new normal life. So we'll see, maybe we'll be able to just implement these van pooling services in other areas in Poland and in other countries as well.
So I've seen Broomee, and it's a really great idea. So if we have in the audience people working for local government, strongly advised to contact Paweł, because it's like a really beneficial and really future service, I think.
Yeah.
So my question would be, let's say, what do you take from your academia life into your startup life, and the other way around?
Okay. Well, so working in both domains is quite beneficial, I would say, because when I do a research work, I learn a lot, right? So I also learn about new algorithms, new technologies. I also learn how to design new algorithms and new techniques. And thanks to this, I'm familiar with state-of-the-art techniques, state-of-the-art algorithms, for example, for logistic optimization, right? And then we can easily use this algorithm. We can easily implement these algorithms in real-world products, like in this Broomee service, where in fact our goal is to optimize the logistics. So just to be clear, we are not a company selling or providing buses or vans. We just provide IT services aiming to optimize the fleet of buses and match the passengers with cars, with vehicles, with buses in the optimal way, right? So when we have multiple requests from passengers willing to travel from point A to point B, and we have many vehicles that can just serve our passengers, the question arises how to optimally match these passengers with vehicles, and how to say which vehicle should travel where, when, in which order, and so on. And mathematically, or from the perspective of theoretical computer science, it corresponds to the so-called dynamic capacitated pickup and delivery problem with time windows. So again, it's a difficult name, but there is such a mathematical problem in computer science. And what's interesting is that it has been proven that this problem is NP-hard. So again, it's most likely classical algorithms will not be able to solve it in an efficient way. And there is a hope, but I just want to emphasize that there is only a hope. It also hasn't been proven, but there is a hope that quantum computers will be able to solve such optimization problems more efficiently. And this is also one of the reasons why I also do research on quantum algorithms for this logistic optimization. I can say that beside Broomee Technologies, which is also intended to optimize the transport of people in cities, I'm also collaborating with another startup, Polish startup that is called Snarto. And in this startup, our goal is to optimize logistics, logistic or transport of products, right? So in this case, again, we have some companies or people willing to deliver some products from point A to point B or to many other points. And at the same time, we may have multiple companies, multiple logistic or transport companies having some trucks that can be used to just, can be applied to just pick up some products from one place and then deliver to another place. And then again, the question is how to match these customers with fleets in the optimal way, right? So it's mathematically, it's very similar optimization problem, but the business use case is different, right? So here we optimize fleets of vehicles transporting some products, some goods, some assets, and in a large scale, like the whole Poland or the whole Europe. But in case of transporting people, it's rather extension of the public transportation in the urban areas.
So a year ago, I read a post on something similar on TechCrunch, like Uber for lorries, or Uber for vans for delivering goods. And I think that there must have been another few startups like that in the last 12 months, because I think that this is a huge area for AI ML to optimize. And I remember that day I had a candidate talk. I won't make public his name, of course, neither the name of the company, but he was a CIO of one of the biggest logistics companies in Poland. Not a very nice man. That's why I'm maybe mentioning this. Because when I asked him, let's say, what does he think about, using ML AI in logistics, he says, this is just some gibberish.
So I can say that currently, yes, I can agree that AI is currently, I would say that in the edge of the research on optimizing logistics, because the logistics optimization is the very old problem, right? So it has been investigated for the last several decades. So research work started really many decades ago, and there are already many good classical algorithms like heuristics or meta-heuristics able to solve it in quite efficient way, at least in small scale, because as I said, it has been proven that most of these problems are so-called NP-hard, which means that most likely they cannot be solved efficiently, or we cannot find the exact solution efficiently using classical computers. But recently, in the last couple of years, there have been published several research works showing how to use very new machine learning techniques like pointer networks, encoder-decoder techniques, and reinforcement learning to optimize or to solve these optimization problems, more specifically, mostly the traveling salesman problem and vehicle routing problem. So these problems are still rather simplifications of real logistic problems, but anyway, the research works that are published, that were published during the last 5 years, showed that there might be some advantage of using machine learning techniques in this domain as well, even though this domain have been already was investigated for many decades, right, before.
Yeah, it's fascinating to see, let's say, how real business, real life coincides with science.
Yeah.
I love to see it, because I know some scientists are like, I'm for the pure science,
Yes.
Not to apply this, because this is what science is about. So I'm really glad to see somebody who's taking.
Yeah. So I can say that I was studying mathematics and computer science at the University of Warsaw. It was already more than. So I started my studies 18 years ago already. And at the beginning, I also thought about myself that, okay, I'm a rather theoretical guy. But when I was closer to the end of my studies, I also started thinking more about applications, and I also observed that my mindset also transferred from being a mathematical or working on mathematical theory to just applications and rather focusing on computer science and IT. And at the end of my studies, I did software engineering internship at Microsoft in Redmond in the US. And I was even considering going back there to the US to work there for a full-time job because I got the offer and even the visa to work in the US. But I decided to stay in Poland and do research. Then I did some other engineering internships at Google, in CERN, and in IBM Research in Ireland. And I also started collaborating with some businesses, with some companies here in Poland. Later, mostly as an advisor, consultant. So that was my role. And currently also, I work mostly as a mentor, advisor, or leader of some engineering or research teams in some R&D projects. And thanks to that, I have quite good connections and also good experience in just collaboration with business, both in Poland and in other countries. I like it, right? So from one side, I feel that the theoretical mathematics and theoretical computer science are already quite matured, I would say. So it's very difficult to just achieve a significant advancement in this domain, in the domains of theoretical math or theoretical computer science. There are still some open problems, which are very interesting, but also very difficult, because these open problems, so most of these open problems are known for many years, right? Like 50, 60 years. And the fact that they are still open means that they are very difficult because there were already hundreds of thousands of very smart people working or spending almost the whole life just to solve these problems, right? So these problems are very difficult. And at the same time, there's just there are more and more real-world applications, and I would say that just figuring out how exactly some new technologies like AI and quantum computing can be applied in various domains is also very interesting and very challenging. And having this knowledge from science, how exactly some new algorithms and new technologies work, is very helpful when we think about some potential business applications. So this is another advantage of just combining or working in business and science at the same time. Another advantage is that I still have classes with my students at the University of Warsaw. So I still teach people, and people coming to study computer science at the University of Warsaw are very smart. Some of them are just winners of some Polish or even international contests in computer science. So then I have also connections with those people, and I can propose them some very interesting projects. And these are people who really look for really challenging, difficult, and cutting-edge projects. So they are not interested in just I don't know, developing new websites or administering servers, or just doing some, let's say, standard engineering work, but they are actively looking to just work on such cutting-edge projects. And about 10, 15 years ago, there were not that many advanced projects in Poland yet. I think that now there are much more interesting projects, interesting research projects, and some R&D departments, even in Polish companies or in companies in Europe. So I can observe that the students are also very interested in just learning more about quantum computing and AI machine learning. So it's another advantage, right? So it's also easier for me to just recruit smartest people.
This is a very interesting topic, very touching topic actually to me, because Polish IT market is huge. Poland is one of the biggest IT services markets in the world, not only in Europe. And for years, I've been an IT recruiter and talked to very many high-level executives, and from the big tech, from the big names, also from the outsourcing companies, like for instance HCL or Capgemini or that kind of companies. And everyone said until some 5 years ago, Poland is fantastic nearshoring, offshoring market, but it's relatively expensive, but people are there and they are everywhere. In Poland, we do have all the skill sets that we need, and still value for money is excellent. But it's a high-end offshoring market, not like cheaper Asian locations, but it is still offshoring market. So it's not a place where we build products, where we create real value. We just outsource to Poland. And yes, this is the bad thing. The good thing is that it is changing.
Yes,
it's changing for the good. We have our unicorns. We have absolutely fantastic people like your students or yourself who do cutting edge, world class technology. But I don't know if we keep the pace enough, so that we would develop, more our startup community, our startup environment, let's say cutting edge technology companies. I'm just wondering why it's so. What's your opinion on
that? So it's very interesting, and it's good that you are asking, because in fact I have one interesting opinion on this topic, because I observed that people in Poland are still very skeptical, I would say, in terms of new technologies and investing in new technologies. Maybe one of the reasons is that we don't have so much money as, for example, in the US. So we are more cautious, right? And we don't want to take risk and invest money in risky initiatives. But it's very difficult to find people willing to invest in quantum computing here in Poland. So I was recently, I think I was contacted by at least 2 or 3 venture capital companies investing in quantum computing and actively looking for some startups operating in the quantum computing domain here in Poland. And there are not that many startups. So I know several companies, and some of them are really very good and world class as well. But it's still a relatively small market. And I think that one of the reasons is that, so for example, when I talk to some people from my university, they told me that, or some of them told me that they don't want to work on quantum computing because there are still not, we still don't have real quantum computers, and it's still possible that there will be no quantum computers in the future. So okay, it's reasonable, right? So when you have many other options, when you are a computer scientist, you have options to work in the AI, when the applications of AI are already proven, right, and are already on the market. So it's something when you have almost no risk. So it's almost or very small risk, right? So it's almost certain that okay, you will be able to just build the technology and later apply this technology. So there is no risk, and you may have benefits. In case of quantum computing, there is still a risk involved. As I already told you, it's still possible that this trend will stop at some point. And I think that people don't want to take this risk. So this is one of the reasons. But from one side, of course, this is something understandable, because when you have 2 very good options to just build a startup working in the AI sector, and when you have almost no risk, and the technology is already proven and advanced, and to build a startup in quantum computing domain when there is a huge risk involved, the potential revenues are the same, or maybe even we can expect more revenues in case of AI applications. It's natural that you chose to work on projects that are related to AI and focus on AI and not in quantum computing. But in other countries, I think that there are more people who really actively look for such very, very risky projects. Like, for example, in the US, in the UK, right? So I believe that probably the availability of money and the value of money is also a bit different, because if you have billions of dollars, then investing 1 million is not a problem for you. When you have only, let's say, 10 millions, then investing 1 million is something that you should really analyze and consider, right? So this is probably one of the reasons. But the consequence is that if at some point there will be this true quantum supremacy and quantum advantage, again, we'll say that, okay, Poland is not prepared, that we have to import technology from the UK and the US because they were investing for 10 or 20 years in quantum technology. They just took this risk and they already have this technology advanced and developed. And in Poland, we don't have technology and we don't have know-how. And it was the same with AI, right? So I can say that I was interested in AI and machine learning even in 2005, 2006, when I was just starting my studies in math and computer science. I already knew that AI and machine learning is something that I would like to be involved in somehow, right? And I was teaching machine learning at the University of Warsaw in 2011, before machine learning was popular. And there were also many skeptics of machine learning and AI before this hype that started about 2012, 2014, 15, right? Yeah. And again, but there were only a few people like me willing to work on these very risky technologies then. And the effect is that again, as we had to just rather follow the technologies and follow the companies that were really on the edge of advancements in case of AI and machine learning. And we had to just build this machine learning and AI market almost from scratch. And we're already a few years behind some companies in the West. And in case of quantum computing, it might be the same, right? So we don't want to take the risk now. And the reason or the consequence in a 5-10 years from now might be that we'll say again that, okay, the whole civilized world, the West, the US are just behind us, many years behind us, because we just didn't invest in quantum computing when the risk was higher, of course. So I believe that one of the reasons of this being more risk averse, I would say, is the availability of money, probably. So that's one of the reasons.
This is an interesting thing, because let's say now the power of deep tech is in China, in my very opinion.
Yes, I agree.
Investing in quantum computing?
Yes, I think it's the same in quantum computing. So you said about this experiment with quantum supremacy that was carried out by Google in 2019. But I think that a couple of months later, if it was 2020, there was a similar experiment, but the design of quantum computer was different, and also the use case was a bit different. And it was carried out by researchers from China, indeed. So it's another example of, let's say, quantum supremacy or quantum advantage. So just maybe coming back to these experiments, as I said, these experiments or this advantage was proven just for some very specific applications of quantum computers and very specific artificially designed use cases. So currently it's rather, or it's believed that this is something like the first flight of the Wright brothers, when I think that the distance was about 280 meters. So this is the distance that we can just cover cover by feet or by bike. But they proved that it's possible, and later, in 10 or 15 years later, we had commercial flights.
Only.
So yes, right. And now, so in fact, we already also have commercial quantum computers, but we don't have a real commercial advantage, business industrial advantage of quantum computers yet. But it may happen that there will be such an advantage in 10 or 15 years from now.
Paweł, last question. You also run a foundation.
Yes.
Can you tell us something more about it?
Okay. Yes, I'm the founder and CEO of the Quantum AI Foundation. So it's a non-profit a charity organization supporting research, education, collaboration in new technologies, especially quantum computing and AI. I found that this NGO, in order to just support organization of our activities, because I'm one of the organizer of a meetup that is called Warsaw Quantum Computing Group meetup. We also organize and we even sponsor. So this is interesting that as the Polish non-profit organization, we also we are also a sponsor of a quantum computing meetup in Washington, in the US. So we organize this meetup together with people from Washington and from Toronto. We also organize workshops, and in these workshops, we teach people how to write quantum computing programs that can be later run on real quantum computers that are available in the cloud or on simulators of these quantum computers. Last year, we also organized the first, I think it was the first hackathon on quantum computing in Poland. It was a hackathon on developing quantum games. We also organized a conference on quantum machine learning together with researchers from India. So there were people from Poland and India involved. And we also organized some contests. So this year, we have now the second edition of a contest aiming to popularize quantum computing. So this contest is addressed to high school students and university students in Poland. So the goal is just to prepare some popular science works like art, right? Like computer games, computer programs, books, comics, anyway, or any tools for popularizing quantum computing are allowed. And last year we also organized the first programming contest on quantum computing together with Polish Department of IBM and together with Polish division of BNP Paribas Bank. So there was just a specific programming task for participants, and the goal was just to build, let's say, the smallest or the cheapest possible quantum circuit solving the given problem.
Fantastic.
So these are the initiatives that we organize. We have 3 people in the board, 3 people in the advisory board, and our goal in general is to build this quantum computing ecosystem here in Poland, but we also collaborate with similar groups in other countries. So there is an international initiative that is called QWORD, and currently I'm also serving as a vice chairperson of this QWORD initiative. So formally it's an association established and registered in Estonia. Indeed, we collaborate together to prepare educational materials, to organize some events together, like organize workshops or hackathons or webinars, conferences together. And there are currently more than 500 people involved from the whole world.
Wow.
Besides, I've also founded and I moderate several Facebook groups related to quantum computing. So one of them is Quantum AI. So there is such a Facebook group called Quantum AI. So this is the group that I founded in 2018, and there are now more than 5,000 people from the whole world. So that's very interesting. There are also some other groups like Q Poland, Warsaw Quantum Computing Group. So these are just initiatives that I organize, not only by myself, but I also collaborate with many other people from Poland and also from other countries. So if someone is interested, of course, we invite you to join us. So feel free to reach me out. I will be happy to just talk with you about potential collaboration. And since we are a non-profit organization, it's also possible to donate our activities. So please visit the website of the Quantum AI Foundation, and
I will put
there are some options on how to donate. Mm-hmm.
I will put into the comments all the details of the foundation.
Yes. Yeah.
So I think that we could go on and on, but we have limited time. I'm extremely appreciate having Paweł today, a true Renaissance man. And
thank you,
Paweł. Thank you so much for this podcast, for this episode.
Thank you.
And we stay in touch.
Yes, thank you very much. Thank you once again for the invitation. It was my pleasure. I like talking about science and quantum computing, so I hope that all people enjoyed. Thank you very much.
Have a great day.
Have a great day. Thank you.